Hello everyone, welcome back to another episode of Study Smart. In our previous video, we talked about the very first method of solving the non-homogeneous ODE, which we solved some problems on it. And in today's video, we are going to be talking about the second method, which is the method of variation of parameters. Right, so we'll be talking about method of variation of parameters. The idea about this method is just very simple. I'm going to give you some basic steps to use in terms of solving a non-homogeneous ODE using this method. We'll just go down here, basic steps. Right, so basic steps. Firstly, in solving a non-homogeneous equation using the method of variation of parameters, the first method you are going to employ, the first step you are going to employ, you are going to solve, you are going to find the complementary solution using the initial way we know or have learned on how to solve them with. So firstly, you are going to solve the homogeneous part. You're going to solve the homogeneous part to obtain yc equal to c1 exponential m1x plus c2 exponential m2x. Alright, so we are going to solve this in this form. And then after we've done that, we are going to replace c1 and c2 by another constant. You can say you can choose any constant of your choice. Right, so secondly, you are going to replace c1 and c2 by another constant. Let's say let me use u1 and u2 in place of c1 and c2. Right, so we're going to replace c1 and c2 by another constant, u1 and u2, to obtain yp. Right, so if I replace that in this form, I'm going to have u1, right? I'm going to have u1 exponential m1x plus u2 exponential m2x. Right, so because we assumed that what I can say here, recall from our initial classes, I told you that in solving the auxiliary equation, you should assume y to be equal to exponential mx. Alright, it means that my y1 here is exponential m1x and my y2 here is exponential m2x. So I can replace exponential m1x by y. Right, so I can assume my solution yp to be equal to u1 of x y1 plus u2 of x y2. Right, so this is the kind of solution we are going to obtain for yp. We are going to assume yp in this form. Then the next step 3, you're going to find the value of u1 and u2. Right, so you're going to find u1 and u2. Right, you're going to find u1 and u2 using using u1 prime. Right, u1 prime equal to w1 over w and u2 prime equal to w2 over w. Right, so in order for us to find this, we have to look for this first and then look for this first. And after we've done that, All right, so the U1 here, let me start from the the W. So I can say where W, which is a wrong scan, will be Y1, Y2, and Y prime 1, Y2 prime. All right, so this will be W, and W1 will be given by 0 f of x and then y2 y prime of 2. That's for W1 here. And then W2 will be given by y1 y prime 1 then 0 f of x. Right, so we are going to obtain this, then we substitute it in order for us to get this and also get this. Right, so the third step here, after you've gotten u1 prime, you are going to integrate. Right, so integrate u1 prime and u2 prime in order to obtain u1 and u2. Right, in order to obtain u1 and u2. Then thirdly, and lastly, after you've obtained this, you substitute it back to this equation, then you obtain your general solution. The general solution y equal to yc plus yp. Right, so this is the simple step to follow in order of solving a non-homogeneous equation using the method of variation of parameters. First, you are going to solve the homogeneous part to obtain y complementary. You are going to replace C1 and C2 by another constant. Let's say I used here U1 and U2 in order for us to obtain YP. And I deduced YP to this form because I said in the initial video that y is equal to exponential mx. So I replaced exponential mx by y here. Then after, we are going to look for U1 and U2. But before we look for U1 and U2, we have to look for U1 prime, which is given by this, and then U2 prime, which is given by this. And I also give you the run scan, and then the first run scan and the second run scan, which we are going to substitute to this expression in order to get this and get this. And after we've done that, we are going to integrate u prime 1 and then u2 prime in order to obtain u1 and then obtain u2. And after we've done that, we are going to obtain the general solution y equal to yc plus yp. Right, so we are going to follow this step exactly, and then we are going to take an example in order for us to illustrate this method of non-homogeneous equation solution. And so we are going to be taking a very quick example. All right, so we are given the question, which is 224 past question or engineering question number 7 of the question mathematics. So given the differential equation, the square y over dx squared minus y equal to 2 exponential minus x, right, with some initial conditions, y of 0 equal to 1 over 2 and y prime of 0 equal to 1 over 2. And we are asked to find, using the method of variation of parameters, the auxiliary equation, complementary function, and the particular integral, and as well as the general solution. All right, so this is our expression here. And then from the initial rule I gave you earlier, I told you that the first step, you're going to look for the complementary function. And in looking for the complementary function, on our way, we will be answering question 1, which is the auxiliary equation. Right, so we need to form the auxiliary equation first before we can be able to look for the complementary function. Right, so we are going to look for the complementary function now by equating the left-hand side. Alright, turning this equation homogeneous by equating the left-hand side to 0. So this is what we are going to be having. And then after, we are going to let y to be equal to exponential mx, and then we differentiate y equal to exponential mx twice, because the highest power here is 2. So we are going to be differentiating y here twice. And then in course of differentiation, we got dy over dx to be m equal m exponential mx, and we got d square y over dx squared to be m squared exponential mx. And then after, we going to substitute the value of d square y and then y to this expression. And when we did that, we obtained this, because the square y over dx squared is m squared exponential mx, which is this. Then I have a minus sign. My y here is exponential mx, which is this. And then I factor that m squared minus, I factor that exponential mx out, because exponential mx times s squared will give me this. Exponential mx times 1 will also give me this, equal to 0. So provided that exponential mx here is not equal to 0, I will bring out this equation to obtain m squared minus 1 equal to 0. Alright, this is what I'm going to be obtaining here. So if I move minus 1 across equal to sign, I will be obtaining m squared equal to 1. Alright, so this is square root. I'm going to take the square root of both sides. If I take the square root of both sides, I'll have m to be equal to plus minus square root of 1. Alright, so I'm going to be obtaining square root of 1, and the square root of 1 is 1. Alright, so my m here is equal to plus minus 1. So it means that I have two solutions here. I have plus 1 and I have minus 1. So it means that my m1 is equal to plus 1 and my m2 is equal to minus 1. Right, so we have already succeeded in answering question 1, which is the auxiliary equation. Right, so the auxiliary equation we obtained was this, and further deduced to this. So this is the answer to question 1 problem. This question 1. Right, so this is the auxiliary equation, which is further deduced to this. Alright, so the second question there says to find the complementary function. Right, so we've gotten m1 and we've gotten m2. Right, so the question II, which is the complementary function, yc. The complementary function in this case is given by y complementary equal to c1 exponential m1x plus c2 exponential m2x. Alright, so y complementary here will be equal to my c1 exponential m1 here is 1, so I have x, then plus c2 exponential m2 here is minus 2, so I have minus x. So that is the solution for question 2, complementary function. So we've gotten the auxiliary equation, which is this, and we've gotten the complementary function. Right, so we are going to be diving into getting the particular integral. And from the rules I stated earlier, I said that we have to solve the homogeneous part of the ODE, which we did, and we've obtained this. And then secondly, we are going to replace C1 and C2 by another constant using any constant, and I'm using U1 and U2 in order for me to replace this. So we are going to dive into solution 3, which is a particular integral. So particular integral yp. Right, so we'll be working with the rules I gave earlier. I said we are going to replace C1 and C2 by another constant, say U1 and U2, in order for me to obtain this. Right, in order for me to obtain this, which I further deduced to this. So we'll be making use of this. So we're going to assume yp. We're going to assume yp to be equal to we're going to assume yp to be equal to u1 of x y1 plus u2 of x y2, which is for the second step, which is this. I assumed it. It's already in the step. You just assume it this way. All right, so after replacing c1 and c2 by u1 and u2 here, the next step there says we should find u1 and u2 using this expression. Right, so we are going to obtain u1 prime and then u2 prime. Right, so let's obtain u1 prime. So we are going to obtaining u1 prime and u2 prime. And I told you earlier that u1 prime is given by the first Wronskian w1 over the general Wronskian. All right, so that's u1 prime. So we are going to look for first the general Wronskian. So the general Wronskian, like I said earlier, is given by y1, y2, y prime 1, y prime 2. Right, so from this case, we'll be making use of our complementary function here. So these are our y1, these are y1, and these are y2. Because I said from the law, I deduced from the law exponential mx and exponential m1x and exponential m2x to y1 and y2, which is here. After replacing it, I got this. So my y1 here is this, and my y2 here is this. So in this case, because we've gotten the complementary solution, my y1 becomes this, while my y2 becomes this. Right, so we are going to go back to the question, the solution. So y1 is equal to exponential x, and then y2 is equal to exponential minus x. So the Wronskian of this thing, this expression, which is exponential x and exponential minus x, will be y1, which is exponential x. This is exponential x, and my y2, which is exponential minus x. So this is exponential minus x. So I'm going to take the differential from here. So this is y prime 1. So I'll take the y prime 1 of this. If I differentiate exponential x, I will obtain exponential x. If I differentiate exponential minus x, I will obtain minus exponential minus x. Right, so I've succeeded in expressing this in determinant form. So I'm going to solve this. So the Wronskian of this becomes equal to, this times this gives me minus exponential minus x times exponential x, then minus this times this, exponential minus x times exponential x. Right, so from the law of indices, the bases are the same. I'm going to have minus, the bases are the same, I'll pick one, then I'll add up the powers. This is exponential. Minus x plus x here gives me 0. Then I have minus, I have exponential because the bases are the same. Minus x plus x here gives me 0. And this is going to give me, anything raised to power 0 is 1. So I have my minus sign here. This is minus 1. And this is also 1, because anything raised to power 0 is 1, apart from 0 to power 0. So I also have my minus 1 here, which is going to give me minus 2. Alright, so the Wronskian W here is equal to minus 2. So we are going to keep this aside. We've gotten W. So the next step here we are going to look for is W1. So W1 from the expression I gave is equal to the determinant of 0 f of x and y2 y prime 2. Right, so I'm going to have equal to my 0, my f of x was given from the question Right, so from the question I was given my f of x. Right, so from our question, this is my f of x here. 2 exponential minus x here is my f of x. So I'm going to replace that here. 2 exponential minus x, which is my f of x. Then my y2 is this. This is exponential minus x, and my differential of y2 is this, which is y2 prime. So this is minus exponential minus x. So I'm going to obtain w1 here to be equal to, so this is 0 times this is going to give me 0. I have 0, then I have minus. Right, so this times this is going to give me 2 times exponential minus x, and then exponential minus x here. Right, so I'm going to have, this is 0, it's gone, so I have minus, I have 2 here. So the bases here are the same. I'm going to take one of the base, and I'm going to add up the power. So minus x here gives me minus 2x. So this is minus 2x. Right, so my w1 here is equal to minus 2 exponential minus 2x. So this is my w1. So I'm going to replace my w1 and my w to this expression in this point. So it means that my u prime 1 is equal to w over w1 here is equal to, right, so my general run scan w is minus 2. Right, sorry, this is w1. Right, so I have w1 over w. So this is w1 over w1 over w. Right, so my w1 is this. So I have my minus 2 exponential minus 2x over, I have my general run scan, which is w, to be minus 2. So I have minus 2. So my u1 prime here is going to give me, this is minus 2 and this is minus 2. So these two can cancel out. So I'm left with exponential minus 2x. So it means that my u1 prime is equal to exponential minus 2x. Alright, so next up here from the rule, we've obtained u prime 1, and then we are going to integrate u prime 1. Obtain, he said find this, and then you integrate them in order to obtain u1 and u2. So we are going to find this, which we have done, and then secondly, we are going to integrate it. We are going to integrate the value we've gotten. Right, so we've gotten u prime 1, that's du over dx, u prime 1, which is equal to exponential minus 2x. So we are going to integrate this in order for us to get u1. So integrating u1 prime to obtain u1 here, we are going to be having the integral u here will be equal to u1 here will be equal to the integral of u1 prime, which is equal to the integral. Right, so u1 here we got was, these are u1 exponential minus 2x. So I will look for the integral exponential minus 2x. This is exponential minus 2x. So I'm going to integrate this. Alright, so how do I integrate exponential minus 2x? The cheat here is very simple. I'm going to divide the integrand, which is this, by minus 2. Right, so the integral of this will be exponential minus 2x over minus 2. Right, so that's the integral of this. If you check very well here, what I just did was I pulled out the -2 here and I brought it down. Alright, so this is also the same thing as having. Alright, so this expression can also be deduced in the form of -1/2. Then I have exponential -2x. Alright, so it means that my u1 after integrating gave me -1/2 exponential -2x. So I'm going to keep this. We are going to keep this. So next up, we are going to look for u prime, u2 prime. Alright, we're going to look for u2 prime. I told you that from the law, we've looked for u1 here. Next up, we are going to look for u2. Right, so I gave you expression for u2, which is w2 over w. So w2 here over w. We already know our Wronskian, which is -2, so we are going to obtain w2. And I gave you expression that w2 is equal to the determinant of y1 and then y1 prime and then 0 f of x. Right, so I'm going to have equal to my y1 I'm going to look for my y1 from our yp. Right, so from this point, this is my y1 exponential x. So my y1 here is exponential x and my y prime 1 is exponential x. I have my 0 and my f of x here. My f of x is -2. Integrating u2 prime here, I'm going to have u2 equal to u2 prime here, which is -1. I'll have the integral of -1. Right, so this is dx. I forgot to add dx at the other part, so this at dx. Alright, so integrating with respect to x. So this is dx. If I remove or bring out this minus sign out of the integral sign, I will be having minus integral 1 dx. So if I integrate 1 dx, I will be having x. Right, so it means that my u2 here is equal to x. So I've gotten the value for u1 and I've gotten the value for u2. So the question 2, which is to obtain the y particular as a particular integral, we are going to recall that yp is equal to u1 of x y1 and then plus u2 of x y2. Right, so we know the value of our u1 and we know the value of our u2. We'll just substitute them here in order for us to get the y particular. So yp from here is equal to my u1 is -1/2 exponential -2x. So this is -1/2 exponential -2x we have times y1. So from here our y1 is exponential x, then plus u2 here, which was obtained to be this, which is x multiplied by y2, and y2 is given by exponential minus x. So this is exponential minus x. Alright, so we can deduce that we can write our yp here to be so our yp, therefore yp is equal to, this is exponential x, right? So This is exponential x, and we have exponential minus 2x. So the bases here are the same. I have minus 1 over 2. So this is exponential, and this is exponential. I'll take one of the exponential. I'll have exponential. I have minus 2x and I have x. So these two can add up. So minus 2x plus x here is going to give me minus x. So that's for this. Then I have plus x exponential minus x. Right, so if you check very well from this point, exponential minus x is common, so I can factor it out. So my yp from here is equal to exponential minus x into x minus 1 over 2. Right, so this becomes the answer for yp. Then the last rule says that after you've obtained your particular integral, you are going to look for the general solution, which is from the last question we were asked to obtain the general solution. So the general solution, which is IV, right? So question 4, IV, which is the general solution. General solution is y equal to yc plus yp. So we already know the value, the expression for yc, which we've gotten. Right, so we obtained yc to be c1 exponential x and c2 exponential minus x. So this is c1 exponential x plus c2 exponential minus x. Then plus yp, and this is our yp. So we'll have plus exponential minus x, x minus 1 over 2. Right, so this becomes the general solution of the expression. If boundary condition was not given, you can end your answer here. But because boundary condition was given from the question, we'll still continue in order for us to find C1 and also find C2. Right, so from the question, we were given initial condition y of 0 equal to 1 over 2 and y prime of 0 equal to 1 over 2. Right, so since initial conditions were given, you can just come over here to say recall initial conditions. Recall initial conditions y of 0 equal to 1 over 2 and y prime of 0 equal to 1 over 2. Right, so the task here is very simple. We already know our y, which is this. The idea here is that we are going to substitute 1 over 2 to this expression. Alright, we'll substitute 1 over 2 to y, and we'll substitute 0 to x. This is x and this is our y. Alright, this is our x and this is our y. Right, so my y here is 1 over 2 from this expression. So from this expression, I will have 1 over 2 equal to, so I'll substitute x here to 0. So I have c1 exponential to power 0 plus c2 exponential to power 0, because 0 minus 0 is also 0. Then plus exponential to power 0 into 0 minus 1 over 2. Right, so yeah, I'm going to have from here 1 over 2 equal to, this is giving me c1 plus c2 plus here will give me 1. I have into 0 minus 1 over 2. So 1 over 2 from here is going to give me c1 plus c2, then plus this times this will give me 0. Alright, so here is going to change to minus because here is minus. So minus 1 times this. Alright, so 1 times this is 0. Alright, so I'll have minus, I'll have 1. This becomes a mixed fraction of the form 1 whole number 1 over 2. Alright, so this is minus 1 whole number 1 over 2. Right, so in turning a mixed fraction into an improper fraction, we multiply this times this plus this, then all over the denominator. Right, so 2 times 1 is 2, plus 1 is 3, then over 2. Here becomes 3 over 2. Right, so I am to obtain the value of C1 and C2, so I will move minus 3 across the equal to sign to rewrite this in the form C1 plus C2 equal to, this is 1 over 2 here. If this minus sign crosses here, changes to plus, I have 3 over 2. So my C1 plus C2 here is equal to, this is 2. Right, so 2 cancel 2, I'm left with 1. 2 cancel 2 here, I'm left with 1 times 3 here, I have 3. Right, so C1 plus C2 here is equal to 1 plus 3 here gives me 4. 4 divided by 2 gives me 2. So let's call this equation 1. Right, so we are given another initial condition of y prime of 0 equal to 1 over 2. It means that we are going to differentiate this to get y prime. So from the general solution, the differential of the general solution, y prime here becomes equal to, if I differentiate this, I will have C1 exponential x, because the coefficient of x here is 1. So 1 times the whole of expression here is still 1. Alright, so it's still the same thing. So I come here, the coefficient of 1 here is minus, the coefficient of x here is minus 1. So minus 1 times this expression, this sign will change to minus. So here turns minus. I have C2 exponential minus x. Then I have, if I differentiate this thing, right, so I'm going to open up this bracket so we don't get confused. Right, so we don't get confused here. So in opening up this bracket, I am going to obtain back this. So I'm just going to differentiate from here. Right, so if I differentiate this part, because this point and this point, they are the same, so I will just differentiate from here. So if I differentiate this expression here, this minus will multiply the whole of this thing, so this will change to plus, and I get back the whole of this expression. Right, so I'm going to have a plus 1 over 2 exponential minus x. And if I differentiate this point, I'm going to use the product rule, because this is a two function. So the product rule is u dv, this is u, plus u, then I have dv, differential of this is minus of this. So here becomes u dv, that's minus x exponential minus x. Then I have plus v du. So this is v and this is our u. So v du. Right, so this gives me plus exponential minus x. So my y prime here gives me equal to c1 exponential x minus c2 exponential minus x. This is plus 1 over 2 exponential minus x. Then plus times minus here gives me minus. I have x exponential minus x. Then I have plus exponential minus x. Right, so if I check very well from this point, exponential minus x is common, so I will still factor it out. So my y prime here becomes c1 exponential x minus c2 exponential minus x, then plus exponential minus x is common, so I'm going to have exponential minus x into, I have 1 over 2, I have a minus x, then plus 1. So but the initial condition given at this point is, can say, but y prime of 0 is equal to 1 over 2. So I'm going to substitute y here, y prime to 1 over 2, then my x to 0. So if I do that, I will be obtaining my expression to be, my y prime here is 1 over 2 equal to c1 exponential, y here, x here is 0, so I have 0, then minus c2 exponential to power, x here is 0, I have 0, then plus exponential to power 0, x here is 0, then into 1 over 2 minus 0 plus 1. Right, so I'm going to have 1 over 2 equal to, this becomes C1, this becomes minus C2. Then I have plus 1. Yeah, this becomes 1. Then I have 1 over 2 plus 1. So I'm going to solve these inside the bracket first. If I do that, I will be having... Alright, so I'm going to solve this inside the bracket first. So I have 1 over 2 equal to C1 minus C2, then plus 1 times... Right, so the LCM here is 2. I'll have 2. Alright. Right, so 2 cancels out 2 here. I have 1. Right, so 2 cancels out 1. I have 2, then times 1 here gives me plus 2. Right, so 1 over 2 here will be equal to C1 minus C2 plus 1 into this plus this gives me 3 over 2. Right, so 1 over 2 is equal to C1 minus C2, then plus 3 over 2 here gives me 3 over 2 times 1 gives me 3 over 2. So I'm going to cross 3 over 2 across the equal to sign to meet this. So I'm going to obtain C1 minus C2 equal to 1 over 2 minus 3 over 2. Right, so I will obtain C1 minus C2 equal to, the LCM here is 2. This is 2. This cancels out, gets 1. This cancels out, get minus 3. So C1 minus C2 is equal to, right, so 1 minus 3 here gives minus 2. So minus 2 divided by 2 here gives me minus 1. Right, so we can call this equation 2. Right, so from equation 1 here, from equation 1, I can get the value of C1. So C1 from equation 1, C1 is equal to 2 minus C2. So I can call this equation 3. So if I substitute equation 3 to equation 2, I'm going to obtain C1 here is 2 minus C2. So I will obtain, anywhere I see C1, I will write this. So I'm going to have 2 minus C2, then minus C2 equal to minus 1. Alright, so I'm going to be obtaining 2 minus C2, which is 2 minus C2 minus C2 equal to 1. Alright, so this is minus 1. Alright, so this is minus C2 gives me minus 2C2 equal to minus 1. So I can move 2 across to get minus 1 minus 2. So this is minus 2C2 equal to minus 1 minus 2. So minus 2C2 here gives me minus 1 minus 2 gives me minus 3. Right, so if I divide both sides by minus 2, I'm going to obtain C2 to be equal to 3 over 2. Alright, so that's my C2. So if I substitute C2 into equation 3, I'm going to obtain C1 to be equal to 2 minus C2 here gives me 3 over 2. Alright, so my C1 from here, C1 will be equal to, right, so from here, the LCM here is 2. So I'll take the LCM. 2, this is over 1. So 2 divided by 1 is 2. 2 times 2 here gives me 4. Right, so 2 divided by 2 here gives me 1. 1 times 3 here gives me minus 3. Or minus 3. Right, so my C1 from here will be equal to 4 minus 3 gives me 1. I still have over 2. So it means that my C1 is 1 over 2. So C1 is 1 over 2 and C2 is 3 over 2. So from the general solution, so recall from general solution, recall from general solution that y is equal to, from our general solution, we obtained y. From our general solution, we obtained y to be this. So this is our y. So our y is c1 exponential x plus c2 exponential minus x, then plus exponential minus x into 1, right? So into x minus 1 over 2. So that's our y. Right, so we've known the value for C1 and C2, we'll substitute them here to get the solution at initial condition. So y, the general solution at initial condition is C1, which is 1 over 2, exponential x, plus C2, which is 3 over 2, exponential minus x, then plus this, exponential minus x into x minus 1 over 2. So 1 over 2 here is common, so I can factor out. So y here is equal to 1 over 2. I have exponential x plus 3 exponential minus x, then plus exponential minus x into x minus 1 over 2. That becomes the answer to the problem. Right, so in our next video, we are going to be talking about the next method of solving the differential equation. That's the operator D method. Right, so we come to the end of this video. Don't forget to like, share, and subscribe. Thank you.